Happy New Year, everyone! Welcome to the logic tutorial. I'm Router, and I'm going to finish this up. What I've begun in my last logic video. I taught you everything about the instructions, but I haven't really taught you any actual programming yet. Like, you might try to learn some from old definitions and stuff, but we need to actually talk about how do you actually do stuff inside of Ministry logic. So one thing you might start is you might start branching out. So say you want to jump to somewhere when something is enabled and when something is not enabled. Basically like an on-off switch on your code. You can just type in at enabled switch one and maybe assign that to E, just for the hell of it. It might seem like all of those blocks are smaller. That's because I'm playing at my normal UI scale and not the UI scale used for that video. But what you would do next is you would get jump, and this might seem odd because jumps are always like, oh yeah, move to this bit of code. But how do you know that it's actually that bit of code you're jumping to, or if you even have to jump at all? This is where you can compare stuff inside of jumps. So if E equals 0, or actually you could even assign false to it just for readability. Yes, you can have so basically what's gonna happen is if the switch is off, it's going to hit this jump statement right here. It's going to see that, hey, the switch is not enabled, so it's going to jump way back and repeat the cycle until the switch is enabled again. Then you might do some stuff like, actually this is the wrong instruction. You might print hello world, new line. Now you might be thinking, well, why are you adding a new line there? It's completely unuseless, not useful. And what is that \n either? Maybe you don't know what a new line is. And \n is a very special combination. This combination is going to basically say, when you're printing something, turn this into another line. You can just compare it and it'll just print a new line. I'm rambling. So there's actually no switch, but think about this. Because there's no switch, the sensor value is going to be 0 here, always, until I actually place a switch and link it. When I link the switch, it will say hello world and leave a new line again. So this is what's called an if statement or an if sentence. Basically, if A equals B, you can jump to things that actually exist. So you can jump to here, maybe print something, or maybe if that condition isn't true, then you could go on an else branch and do other things here. Now, you may commonly encounter ends instead of jumps, which are also correct because that's also termination. But usually in programming, you would see that an else statement is going to jump back into the main code base. It'll just make your life so much easier when you think about that. The next is the do while loop, and this is the main loop. Now I might see that we've got some very non-standard code here. We're using @links and comparing it inside of a jump. So what we're doing here is we initialize I to 0. This is going to be basically our starting position. This is what our code will execute first, naturally. And then we get the first link, well, zeros, but first, because of how we count from 0 instead of from 1. So you got links 0, 1, 2, and 3, respectively. Now, then you make each one of those links. It's not going to check whether it's a turret or not. is just going to make it try. It's going to try to make that block shoot at an incredibly high Y position. And it's actually shooting, not aiming, so because the shoot equals 1 there. And then it's going to add 1 to I. And if I is less than length, so if I is less than length, it's going to jump back and do it again until I equals length. Why equals? Because if it's less than length, it's just going to increment every time, so you will end up eventually at I being equal to at length, which means that this if statement becomes false. And yes, this is actually still an exotic if statement. You basically just jump right after when it's true. And for readability, again, you might see an end here, but it's completely optional because it will jump back to the beginning anyway. So I equals links, what now? Well, any link that is get linked here would just return null, because that link doesn't exist. If you put at links instead of I here, you'll get null, always. It's kind of a constant there. That's another way you can get null. Which means that you can't iterate through the turrets anymore, and so you have to return. And you return to the beginning of your code, I begins to shoot at 0, and that's it. Now you might be thinking, well, this looks just like shooting upwards, right? I put an incredibly large number here, like 1e40, that's like 10 to the power of 40. If my scientific notation is correct, I don't actually use this kind of notation here, just write the raw value in. You might think that it actually aims upwards. But notice that these duos aren't moving. If I control these duos, I can't move. My mouse is moving, and I still can't. So what I'm going to do is I'm going to give these duos ammo, and that'll activate them. They start spinning. Now, where does this happen? Normally, if I were to put the smaller value here, like 1 to the power of 30, you could see that the duos actually shoot. But if I put 40 in, they just spin. Now, my best guess is that a nuke made a check. Like, if it's like 1e40 is way outside the world. Like, it's not even close to being able to be stored, even on a finite machine. On any finite machine we have, not even on disk. And we have like zettabytes of space now. So why is this called a do-while loop? Well, it's called a do-while loop because you execute things first, and then you jump back while I is less than length. A while loop would just be adding a jump here. So if I is equal to length, actually no, if I is not less than length, so that's greater or equals, then you should jump to over here. If we had a statement here, you would just jump over here and just skip entirely. But that doesn't happen because I is set to 0, so we don't have to do that in this code. But in some other code you might want to do that because for loops are pretty useful. Because, well, this is basically just a for loop, but it also looks like a do-while loop because it just is again. While loops themselves are actually pretty useful for other things. You might find uses for them. I can't name one from the top of my head because I haven't coded in months now. But you can make duo spin. You can make every duo it's connected to spin. Actually, this is dumb. I'm gonna copy this, place it again, and add more duos. They just start spinning. The next construct I'm going to teach you is arrays, specifically memory cell arrays. So, if you take a look at the code here, we can see that we we can see that we have a memory cell configured. So we're going to write 1 to the first and second positions of that memory cell. Why are we writing 1 there? That's because that's what the Fibonacci numbers start at. They start at 1 and 1. Then we're going to set index a variable to 2, and we can derive a and b from there. A and b are going to be the numbers directly before index, so these are the numbers you're going to add together to get the value you're going to put at that location. Which is what we do. We get the locations, and then don't be scared by this, but what it's going to do is it's going to take this value A, this one, and then it's going to take whatever address this is pointing to, and then write that to A. So it would be better to write this as A underscore than add A underscores between them. But I like to reuse variables, so we get that. We get the result, and then we write it back to index. And again, we repeat it until index is equal to 64, at which you can't write to memory cells, because once again, memory cells have a storage capacity of 64. Ignore the language. And this will work. Now I have to introduce you to how this looks in code, because believe it or not, this is what the program looks like to the processor. Actually, you can't see anything. I'm gonna make this larger. This is what the program looks like. Now we're writing 1 to the first and second positions, setting index to 2, as always. Then we subtract. That's what op sub means. Then you read, and then you do all the stuff that I said. Now the ordering here is actually pretty weird, so we can see that it's result cell1 index here, right? It still results cell1 index. Holy shit, did a nuke fix that? Yeah, he probably did. The madman. But now we need to introduce you to the jump for. What does this for mean? Oh, this for means that we're going to jump to the 5th line, again, since we're counting from 0. So let's count. 1st, 2nd, 3rd, 4th. Well, it's actually 5th, but because I'm using the set counter here, it's basically 5th line. Basically, it's the part that moves over here. So what does the set AddCounter do? You've never explained it to me. Well, AddCounter is a variable that tells you what line you're on. We talked about that. I'm actually gonna move this message block. So one good way to demonstrate what setting AddCounter does is you can try to print AddCounter, right? So let's just copy this over several times and then print flush to the message. As you can see, nothing's being printed. This writes empty. Why is that? That's because this is the 0th line. So what this line does is it jumps back to the line here, and this really just makes it start over and over and over. So if I write 1 here instead, it's going to jump to this line, which I'm highlighting here, and we should see the output 2, 3, 4, 5. Why do we see 2? Well, that's because we're reading from AddCounter, and it's 1 larger than what's actually in the code when you read it. And this is a quirk, so I can't easily explain it. And what do you know? We see 2, 3, 4, 5. And if we set counter to 2, this does again. You might also see that if you make an operation to add counter to itself, basically this is like setting the counter. You might see that if I add nothing to it, this will still write 2, 3, 4, 5, because when you read AddCounter, it's going to actually read 1 plus counter. And this means that this is basically equal to 0 plus 1, and it just points here. So if we return that, and we add a 1 in there, we can see that it's printing 3, 4, 5, which is 3 prints, so we can know that we jumped to here instead of here. Again, this is just how mlog works. I didn't make this up, and Nuke did. So we've seen memory cell arrays, but what about seeing them in motion? So let's remove this AddCounter, and of course the code will change. That jump 4 will turn into a jump 3 because the first line was deleted, so it has to compensate. This is why there's an error there, by the way. It points to the third line. And of course, using Daltonides' absolutely ingenious mod, LDB, we can see that it writes the Fibonacci numbers. In fact, all of them were just initialized. And that's strange. Oh, that's because the menu is too large. So we can see 1, 1, 2, 3, 5, 8, 13. That's what you would expect from a Fibonacci sequence. And it goes all the way up to this monstrous number, which we can still store normally. But of course, this is the biggest we get, because this memory cell can only hold 64 values. But what about holding arrays inside of processors? What? I mean, you can do it, but actually, let's take a look at the code here. So, we set counter to 0 again. Then we set two values, array 0, array 1, to 1. And actually, I find this to be extremely hard to read, so just right away I'm saying this. So let's remove AddCounter here. Now, if you're wondering what the block above the processor is, it's the message block. Not a cell block. This isn't attached to any. So what is this doing? It does the same thing again, initializing A and B, but this time we write A to the variable array index. And then we set callback to AddCounter plus 1, so we point at the instruction here, this one, which is going to set A to whatever was outputted by the array. But where does this jump lead? If we follow the line, it's going to lead way over here. And this is our first example of a function. This function is going to multiply array index by 2, and it's going to set the counter to counter plus 1 plus whatever we calculated, the offset. If we set it to 0, 0 multiplied by 2 equals 0, so we jump here, and then we can read 0 and 1. Insane. But what we do next is absolutely clever. So we go back to whatever our callback was, our counter here, and this happens to be the A equals array output line. So we basically go back and back. Now, is this an array? This is basically the same thing as we described up there, but it's written way differently, and it's written entirely inside of the processor. In fact, let me just go back into the text editor for this. This is what the entire code looks like. And as you can see, it's pretty long. But this is not really an array. It's actually just a switch statement. I won't teach you what a switch statement is completely, but essentially you have code you want to execute. You have many different cases. You determine those cases. You calculate, is it the first, second, third, or other case, and then you just do whatever I did here. So basically, you take the case number, multiply it by 2, which is the length of this one block, and then you jump to the counter corresponding to it. It's actually incredibly clever, but it results in massive branching. You can see I've got the entire memory cell stored in memory. And I actually copy-pasted this like a bunch of times. I could have generated it with code, but I didn't feel like it. So here we are. We're setting counter to callback, and this switch statement is responsible for reading from the array. And if we jump back into Mindustry here, we go back here, we do the same thing for B, and then we calculate the sum. And we write it into array input this time. And what this means is we're going to write to one of the two arguments the function has. The first argument is actually it's three arguments. That one reading function, like the reading array, we had two inputs. We had array index and we had callback. Callback is basically just wherever you want to jump after you've done it in my code. But here we have three inputs. We have array input. We skip result. We don't even write result. We just write array input. Then we write array index, which, well, obviously we do. And then we set callback to AddCounter +1, so jump to this instruction, which is going to write array input to the memory cell. And this is a result. And then we add a new line, because of course it's way nicer. When we get index up 1, and then we print flush. We print all of the Fibonacci numbers at once into the message block. And then of course, because the writing function starts here, we put an end here so that we don't mess anything up. And the writing does the same thing. We take the array input and then we set it to array 0. And the same thing for every other position in the array. Basically, you're turning instruction space into memory space. And because we removed AddCounter, we can now go back and witness the Fibonacci sequence emerge. Well, not really, because this actually takes a bit longer than writing to a memory cell. But it's mainly because you're not using one instruction to read, you're using many different instructions. And, oh golly, here it goes. That's the entire Fibonacci sequence that we can record. And you may notice that there's actually a limit here. So let's take a look at what's inside the number 7. So let's take a look at what's happening inside of the lowest number. Let me actually get to it first. The lowest number is 7014873. Let's take a look at what number that is. And here it is. Here's the full number. So what happened here? So let me actually zoom out. What happened here? Zoom out again. This isn't the full number written here. So what happened here is we actually ran out of message block spaces. There's a limited amount of characters you can store in a message block. Think of it as a tweet. It has a limited amount of characters. It also has a limited amount of lines, but of course, that's never been really a problem for processors because they just straight up ignore it. But of course, we can see that in the memory cell example, we've written only 44 numbers. And of course, we've got 20 more to go until we reach this monstrosity. So what is the message block limit? Well, let's actually go back into the editor. So let's go into my sources folder. Go to Mindustry, core, source, Mindustry. So this is the main kind of source code of Mindustry, you just kind of jump right through. So let's go into logic block. What is okay, sorry, this is the wrong class. Message block, the Java. The maximum text length is 220. And of course, there's a reason it's 220 and not like infinite. Is because there are issues with packet sizes. This is why if you put a massive schematic down, and I mean massive, like I have an EMP schematic, if you place this in multiplayer, you will crash. And it's not even a question whether you'll crash. You absolutely will crash because the packet size is massive. But you're not going to hard crash like Mindustry does. You're going to do soft crash, so basically disconnect from the server. And with that, I can finally finish my logic tutorial. If you want to take a look at the unit types, well, at what the units actually do, well, you can actually find it very easily. You can go into content, unit types, and you're going to see every single unit described here. You can see all the types. Then you can see that we have units defined, so daggers have a speed of 0.5, rather max speed, maximum health of 140, and they also have a weapon. And then you have maces, which have a slightly larger hit size. You can't sense that. They have armor, they have health, larger than that of the dagger. And that armor is actually really big in campaign, which is why maces are so menacing. But this goes on and on and on and on until you run out of unit types. The last unit type is the block, which is what's responsible for possessing the block. It has no hit size, it can't move, and has 1 health, but it can rotate at 360 degrees per second, or per tick. I haven't read into the code too much. And also can't command anything, and has an item capacity of 0. Before, it had an item capacity of 30. And that kind of make people mad, so it's no longer, you know. Oh, and also it's hidden, so you can't actually see it. And finally, with that, we have finally exhausted logic. And of course, if you want to download the LDB mod, the logic debugger, you can do it by downloading these 2 mods, which I will type here. These 2 mods will allow you to view the memory cell as it is here. And of course I could put it into the description, but nah, I don't want to. You can just type it yourself, because copying is for nerds anyways. And this has been it. And thanks for watching.